Okay, today's lesson is on performing exponential regression. The data below shows the cooling temperatures of a freshly brewed cup of coffee after it's poured from a brewing pot into a serving cup. The brewing pot temperature is approximately 180 degrees Fahrenheit. And what we have here is a T-chart table. We have times in minutes and the temperature in Fahrenheit. So it kind of cooled off just a little bit. So we have 179.5 Fahrenheit. After 5 minutes, 168.7 Fahrenheit, and so on. After 45 minutes, it cooled down to 102.2 Fahrenheit. All right, recall that a model is a good fit for the data when the following are true. The number of positive and negative residuals are randomly distributed around the x-axis with no pattern. And the absolute value of the residuals are small in relative to the data. So recall that you're going to have a graph, or you're going to have a lot of points. You want an even amount of points on both sides of the x-axis for it to be a good fit. All right, determine if the equation y equals 171.462 times 0.0988 to the x power is a good fit to the data. Complete the chart. This information comes from the last table, and we're going to plug in these values for the time into this particular function, the predicted temperature, and then we're going to subtract the difference from the actual temperature. These are the actual temperatures from the coffee. So, for example, after no time, if I plug in 0 here, remember, anything raised to the 0 power is 1. So this to the 0 power is just 1. And you multiply 1 times 171.46, you're going to get that number back. And what we're going to do, we're going to subtract this number from the actual temperature. So when you do that, you're going to get 8, a residual of 8.038. And you're going to keep going through that with your calculator on this chart. You're going to plug in 5 for x and get the predicted temperature, subtract it from the actual temperature. So if you plug in 5 for x here, you should get this result, 161.41, and you can subtract that from the actual time there, actual temperature, and the difference would be 7.29. And you keep going with the process. Now this one, you're going to get a negative because this is larger than that, than the actual temperature, which is okay. Because remember, with the good fit, you have to have positive and negative residuals on both sides of the x-axis. All right, if you plug in 25 minutes, you're going to get this. And the difference is negative 3.29. After 30 minutes, if you plug it into the model here, you should get 119.36. And the difference between the actual temperature is negative 3.06. All right, you plug in 45 minutes, you're going to get 99.59. And you subtract that from the actual temperature, you should get 2.61. Or I graph the residuals. So you just want to approximately look at the residuals. So if you look at the chart, if I plug in 0, that's going to be roughly 8. So we'll put a point at 8. All right, remember this stands for the number of minutes. And this stands for the temperature. Well, this is the residual here that we're plotting. The difference between the actual temperature and the predicted temperature. All right, so at 5 minutes, it was between 8 and 6. This will be roughly there. And let's see, 15 was the negative there, so it goes down here. .24 is negative. So you take your time to plot this, it's going to roughly look like this. And if you notice, you have residuals on both sides of the x-axis. Some are negative, some are positive. Not a strong correlation, though. But you do have residuals on both sides of the x and y axis, which means we can use this as a fit. Is this function a good fit? Well, I would say yes, because the residuals are on both the x and y axis, above and below the x-axis. And the temperatures came pretty close to the actual temperatures in the predicted model. So I would say yes. This concludes our lesson for today.